Imagine a language model not just generating text, but believing something. Not in the human sense, of course, but in a precise, mechanistic way. It holds a posterior belief about the hidden structure behind the words it sees. What if we could map that belief, its shape, its movement, its very geometry, just like a scientist mapping the curvature of spacetime? This is exactly what we're exploring in our new work, the shape of beliefs. We're not just asking what a model knows. We're asking how it knows it, and how that knowledge lives in the high-dimensional space of its internal representations. To study this, we designed a controlled experiment. We feed Llama 3.2 a sequence of numbers, say 1,000 random integers drawn from a normal distribution, n, 500, 100. The model sees these numbers one by one, stringified as text. And here's the astonishing part. By the end of the sequence, it doesn't just predict the next number, it learns the distribution itself. Its next token predictions become a faithful reflection of the underlying Gaussian. But where in the model is that belief encoded? We zoom into the hidden states, those internal activations at layer 14, and apply principal component analysis. What emerges is not a flat plane, not aligned, but a curved manifold, a smooth, continuous surface embedded in thousands of dimensions. Two distinct manifolds, in fact. One parametrized by mean mu, with sigma fixed at 100. Another by standard deviation sigma, with mu fixed at 500. These aren't arbitrary clusters. They form elegant, smooth structures, like ribbons of belief floating in activation space. And crucially, they're curved. This challenges a long-standing assumption in AI interpretability, the linear representation hypothesis. That ideas live in simple, straight lines, directions in space. But here, the geometry is far richer. The belief space is not flat. It's nonlinear. And that changes everything. Now, what happens when the world changes? We simulate a sudden shift. The first 1,000 numbers come from n, 300, 100. Then the model sees a switch to n, 700, 100. The input distribution jumps. How does the model respond? It doesn't react instantly. Instead, it undergoes a two-stage process. First, the mean of its output distribution snaps towards 700, fast. But the variance, a measure of uncertainty, spikes. It enters a high-entropy state. The model doesn't know what's going on. It's confused. Then, over the next tokens, the variance relaxes back to 100. The belief settles. The trajectory through activation space traces a smooth path, first leaping into a region of high uncertainty, then flowing along the manifold toward the new true distribution. This is belief dynamics. Not just static representations, but evolving trajectories between attractor regions. And the model doesn't just react, it adapts. In fact, when we show it a sequence of multiple switches, it learns the meta-pattern of the data. It starts to anticipate changes faster. This is meta-in-context learning, a sign of deeper, more structured reasoning. But now comes the real challenge, intervention. Can we steer the model toward a specific belief? Say, from mu equals 300 to mu equals 500. The standard approach is linear steering. You take the activation vectors from mu equals 300 and mu equals 700, compute their difference, and add half that vector to the original. Simple, elegant, but here's the catch, it pushes the model off the manifold. The result? The output distribution looks like it's at mu equals 500, but its variance is all wrong. It's not a clean Gaussian anymore. The model has been distorted. The shift is coupled, changing the mean accidentally warps the variance. A failure of geometric fidelity. Why? Because the belief manifold is curved. A straight line in activation space doesn't follow the surface. It cuts across it. So how do we do better? Enter linear field probes, a framework introduced by Joachim et al. Instead of training one probe per class, we train a family of linear probes across a continuous parameter space, say, mu from 300 to 700. Each probe is a direction in activation space, sensitive to a specific value of mu. And here's what we find, these probes aren't random. They vary smoothly with mu. Their cosine similarities form a structured matrix, revealing the underlying geometry. They can be interpolated. They transfer locally, but fail beyond a certain distance. This is not just separability, it's a field. A continuous, coherent structure. This field geometry, encoded in the Gram matrix of probe vectors, reveals a deeper truth. The readout space is low-dimensional. Even though the activation manifold is highly curved, the way we read it out is simple. A few principal directions capture the essence. So now we design a better intervention, field-aware steering. Instead of moving linearly through activation space, we move along the field geometry. We use the probe vectors, their eigenstructure and kernel interpolation to define a smooth, curved path, following the manifold. And the result? When we steer from mu equals 300 to mu equals 500, the variance stays stable. The output remains a clean Gaussian. The model doesn't get distorted. The intervention is faithful. This isn't just a technical win. It's a conceptual revolution. Beliefs in LLMs aren't simple directions. They're geometric objects. They exist on manifolds. They evolve along trajectories. And interventions must respect that structure. We tried to model this with a mixture of manifolds. assume mu and sigma act independently, and interpolate their effects additively. But the results failed. The true geometry is more complex, likely due to nonlinear interactions between parameters. This suggests a new hypothesis. Perhaps the model's representations are best understood not as linear superpositions, but as convex hulls, as proposed by the Minkowski representation hypothesis. Concepts as polytopes. Not lines, not planes, but higher dimensional shapes. So what does this all mean? First, purely linear models of representation are inadequate. Even when a feature is linearly decodable, the underlying geometry is curved. Linear steering can break the model by pushing it off manifold. Second, geometry matters for intervention. If you don't understand the shape of belief, your edits will fail, sometimes catastrophically. Third, we can probe and intervene in a principled way. By using linear field probes, we can tile the belief manifold, read out its structure, and steer along it, preserving the integrity of the belief family. This work is grounded in a toy task, numerical time series. But the implications are far broader. If we can map the geometry of belief in a controlled setting, can we do it in natural language? Can we track how a model's beliefs about political ideology, narrative tone, or scientific truth evolve? Can we steer them without breaking them? We don't have all the answers, but we now have a framework. Map the manifold, understand the dynamics, intervene along the geometry. Because in the end, beliefs aren't just stored. They're lived in the flow of activations, the curvature of representation space. And if we want to understand and shape the mind of the machine, we must learn to see it not as a set of vectors, but as a landscape. A world of belief, shaped by geometry, animated by dynamics, and ready to be explored.